In this video, I'm going to expand on the ideas presented in the 3 blue, 1 brown video about linear independence, span, and basis. So watch that video before watching this. In that video, they discuss these concepts in 2 and 3 dimensions and give nice visualizations of how they work. And I highly recommend watching that first because those visualizations will be useful even when thinking in higher dimensions and even when working with vector spaces that aren't Rn. That's really how we want to be thinking about these concepts. But in this video, what I want to present is how do we think about these concepts more symbolically so that we can work with spaces that are higher dimensional or not Rn. And first, we need to talk about linear combination. Linear combinations are this underlying idea behind linear independence, span, and basis. So what is a linear combination in general? If we have a collection of vectors in a vector space, a linear combination of the vectors is anything that you can write as constant multiples of the vectors added together. So that's what a linear combination is. Let's go to an example in R4. So working in R4, just directly computing it, you can confirm that this vector can be written as 2 times this vector plus 3 times this vector. And that means that 4, 6 minus 2, 17 is a linear combination of these other 2 vectors. That's what it means to be a linear combination of some other vectors. You could also see, and this is not too hard to see, that this vector is not 4, 2, 2, 6. If you try to make the middle entries 2 and 2, because of these zeros, you're forced to choose certain coefficients, and you're never going to get a 4 and a 6 here. So this is not a linear combination of these 2 vectors, because there are no choices of coefficients that will give us this as an output. Okay, so that's what it means to be a linear combination in R4. Let's also look at other vector spaces where I'm going to use P3 here. So with polynomials, linear combinations are actually really familiar, I think. It's just what you do in algebra. Now vectors are now polynomials. We're working in P3. So polynomials of degree at most 3, and x cubed plus 3x plus 1 can be written like this. Or in other words, it's written as a linear combination of x minus 3, x plus 1, and 1. And to give a non-example, we can also see that x squared plus 2x plus 1 is definitely not a linear combination of these 3 polynomials, because these 3 polynomials are never going to give you an x squared term. So that's just not possible. So linear combinations, this notion, works in any vector space. We have some vectors, and we're asking, what vectors can we get by multiplying by constants and adding? Those are the linear combinations of those vectors. And we can expand this to say, all right, well, what if we just take all linear combinations of some vectors? And this is our notion of span. And I'm writing these all as finite sets. Everything I'm saying would work for infinite sets, but is not really necessary for us. So if we have some set of vectors in a vector space, then the span of that set, which I'll just write span parentheses all the vectors, there's not really a standard notation here, it's just the set of all linear combinations of the vectors. And what's interesting, and is not too hard to show, is that when you do this, you always get a subspace of the original space. And the reason for this is that you can always get 0 as a linear combination, right? Nothing is saying that these constants can't be 0. So if you make all the constants 0, you always get 0. And then the reason that you're closed under addition and scalar multiplication is when you take linear combinations and add them, you just get new linear combinations. And when you multiply a linear combination by a scalar, you get another linear combination. So in fact, the span of a bunch of vectors is always a subspace of your vector space. Again, I want to look at examples in R4 and in P3. All right, so in R4, let's look at the span of this collection of 4 vectors. And in other words, this is saying all vectors that we can get by multiplying each of these vectors by some constant, maybe 0, maybe not, and adding them all together. This ends up being the set of solutions to the equation x1 minus 2x2 plus 3x3 minus x4 equals 0. You can convince yourself that all of these vectors are solutions. And in fact, if you take linear combinations of these vectors, you get all possible solutions to this linear equation. So it's a subspace of R4, right? The set of solutions to a linear homogeneous system or a single homogeneous linear equation is always a subspace of the underlying space. So this is an example of span in R4. And if we want to look at span in, let's say, P3, if we start with just the polynomials x cubed and x, and we look at their span, so that's all polynomials that can be written ax cubed plus bx, this is a set of polynomials that you've seen before at some point. This is the set of all odd polynomials of degree at most 3. And so this is, in fact, a subspace of P3 because it's a span of a set. Okay, so linear combinations, and then we have this idea of span. It's all possible linear combinations. Now let's talk about linear independence. So linear independence is taking a different take on linear combinations, and it's asking, do we have redundant vectors? Right? When we look at spans, we're asking, what can we get with linear combinations? Linear independence is saying, what vectors do we not really need in order to get new linear combinations? So we say that a set of vectors is linearly independent if none of the vectors is a linear combination of the rest of the vectors. And otherwise, we say it's linearly dependent. And it's important to notice, I think I really like the 3 blue, 1 brown videos, but I don't think that the explanation of linear independence is particularly good because he misses a really important point. We can't just check, is V1 a linear combination of the rest of the vectors? Because it could be that V1 is not a linear combination of the rest of the vectors, but V2 is, or V7 is. And we'll see an example really highlighting that this is true. And when you realize that this is not a simple condition to check, seemingly, because this is k different conditions if we have k vectors, right? If I wanted to check this, I would have to check, all right, is V1 a linear combination of all these? And if it's not, I would have to say, well, but is V2 a linear combination of V1, V3, and so forth? And I would have k things to check. But it turns out, and this happens a lot in math, when you have similar conditions, sometimes you can figure out a clever way to combine them into a single condition. And we can rephrase this. A set is linearly independent if the only solution to the equation where we kind of take an arbitrary linear combination of these and ask, can we get 0, is found by setting all the coefficients equal to 0. So this is an equivalent way of saying that none of the vectors is a linear combination of the rest. Because if we had a solution to this, where some of the coefficients weren't zeros, we would be able to rearrange it so that one of the vectors was a linear combination of the rest. And conversely, if one of the vectors is a linear combination of the rest, we could push everything onto one side and we would get an equation like this that didn't have all zeros. And so we'll see in an example how this works. But this is important. Linear independence, it's not just that the first vector is not a linear combination of the rest. It's that none are the linear combinations of any of the rest. And to do this, we really do have to, or the best way to do it is to put everything onto one side and ask whether we can get 0 without just doing the trivial thing of setting all the coefficients equal to 0. Let's look at examples. So the same set that we were looking at is linearly dependent. And here's why. You can confirm that this is true. The second vector is a linear combination of the third and fourth vector. But importantly, this first vector is not a linear combination of these three. We can't just check that, right? We would have had to go through and check everything, but we can rearrange this by pushing everything to the left-hand side and saying, look, this is the other notion of linear independence. It's the same thing, but it's saying, look, can we add up some linear combination of these vectors to get 0 where our coefficients are not all 0? One of them was, right? I didn't write it down, but the coefficient on this vector, 2, 1, 0, 0, is 0. It doesn't show up. But not all of the vectors are 0. So this is an example of a linearly dependent set. In our P3 example, x cubed and x, that is a linearly independent set. It's a bit harder to think about with polynomials, but this is almost kind of true by axiom, right? When we're working with polynomials, the powers of the polynomial are linearly independent, almost by definition. But that would be a linearly independent set. Okay, so basis is our next concept. So we have linear independence, we have span, and in some sense, linear independence is, or span is saying, what can we get by adding together the vectors in a set? And linear independence is saying what vectors in this set are kind of unnecessary, right? Up here, this vector 3010 or minus 3010 was kind of unnecessary, right? We can just get it from these last two vectors. So what vectors can we get by adding together multiples of these vectors? What don't we need? The notion of basis is that a basis of a vector space is a subset that spans the whole space and is linearly independent. So we can get every vector in the vector space as linear combinations of the set, but we don't have anything unnecessary in that we could have gotten it from the other vectors. Why is this useful? I put this here because it was really more for myself than for you. I mean, I'm gonna say it, but I wanted to make sure I didn't miss this in making the video. Why is it useful to have a set with this property? And this is worth thinking about. I'm not going to prove it or overly justify it, but every vector in V, if we have a basis, can be written as a linear combination of the basis vectors in exactly one way. So if we have a basis, it spans the whole set. So we can definitely write every vector in V as some linear combination of the basis vectors, but we can't do it in two different ways because that would result in linear dependence in the set. And so this is actually a really useful property. There's other reasons that bases are useful, but this means we don't have redundant vectors. We don't have kind of more than we need. Let's go to examples. So we saw that this set is not a basis for the solution set. It spans it, but it has too many vectors. However, we can remove this vector that we decided was redundant, and now we have a basis for the solution set to this. Any solution you can come up with to this linear system can be written in exactly one way as a linear combination of these three vectors because they're linearly independent and they span that set. The space of odd polynomials of degree at most 3, well, what we started with, the spanning set, is also a basis. Right? Every odd polynomial of degree at most 3 can be written as a linear combination of these two polynomials. So we've talked about linear combinations in general, span in general, linear independence in general, and basis in general. That is for any vector space. I want to go back though to just Rn, because with Rn, we have what's known as a standard basis of Rn. There are lots of different bases for any vector space, including Rn. But if we're working with R2, it's common for us to work with the two vectors 1, 0 and 0, 1. This is what's known as the standard basis of R2. And if you've taken physics engineering courses, you would often write this as I hat and j hat, but that's really short-sighted. You might say, why? I mean, we go to R3 and we do I hat, j hat, and k hat, and then I would say, well, what are you going to do when you go to R4? What's your next letter that you're going to choose? What about when we go to R 10,000? Right? It's short-sighted if we're outside of the physics engineering context, right? When we're working in 3 dimensions all the time, it's great to name things letters and to know what they are. But when we're working in situations where we might want to deal with vector spaces that have lots of dimension, it's really short-sighted to name things letters. And so our notation for the standard basis vectors is going to be E1, E2, and so forth. And because 2 is often not a great example, and when we move to R4, I drew this here as well. The standard basis for R4 is this set, the set of vectors where you have zeros everywhere except one entry, and we denote them by, E sub 3 is the vector where the third entry is 1 and the rest are zeros. Just a quick point, this is not redundant notation, it's the opposite of redundant, I guess sloppy notation. These two E1s are not the same thing, right? This is a 2-dimensional vector with a 1 in the first entry. This is a 4-dimensional vector with a 1 in the first entry. They are not the same thing. And so when you use this notation E1, E2, E3, E4, whatever you go up to, it's really important that the context is clear. Either you specifically say something like, E1 is in R4, and then I know you're talking about the 4-dimensional standard basis vector, or that it's just already clear from context. All right, so hopefully that gives you a sense of the value of linear independence, span, and basis, but also some kind of grounding how things work, so that you can approach thinking about these both for Rn and for other vector spaces.